Dear all, in the present video, we are going to discuss in brief about the pass transistor logic. Now, CMOS and NMOS based circuits are steady states and static behavior circuits. Okay, the meaning of this statement is that the valid output levels as static gates and are associated with the steady state operating conditions. Whatever is applied at the input will be referred back at the output. Okay. Therefore, a typical static logic gate generates its output corresponding to the applied input voltages, and after a certain delay of time. Okay, so there will be a particular delay after which the input will be able to generate an output, and it can preserve an output level only as long as the power supply is provided. So if we disrupt the power supply, the output cannot hold its value. Okay, so the disadvantage of this type of circuitry is that it requires a large number of transistors. Okay, and a considerable delay can be produced in the circuit. Now, in the VLSI applications, we require a high performing digital implementation with reduced circuit delay and silicon area. Hence, dynamic logic circuits are preferred. Okay, so we want that circuit should use minimum number of transistors. Okay, and then we want that delay time of the transistor should be reduced. If we will use minimum number of transistors, silicon area will also get reduced. Okay, but this is possible only with the help of dynamic logic circuits and not with the conventional CMOS or NMOS logic circuits. And dynamic logic circuit provides a much better way to implement the digital logic circuits. So, dynamic logic circuits operates on temporary or transient storage of charge in parasitic node capacitance and do not rely on the steady state circuit behavior. Okay, so we all know that dynamic circuits or the dynamic logic circuits which we are going through or which we are going through store use or make the utilization of parasitic node capacitances. Now, what is this parasitic node capacitance? That should be much more clear to you if you are not aware about the concept of parasitic node capacitance. Okay, so we all know that MOS structure is a capacitive structure with metal gate and a N channel or a P channel, and these two metal plates can be assumed to be separated by the dielectric. Okay, so the dielectric material and the combination of both the metals form a capacitance, and this capacitance is required, or this capacitance is capable of storing a fixed charge in itself. Therefore, we have gate based capacitances in all our MOSFET circuits. Since dynamic logic circuit will also be made with the help of MOSFETs, therefore there will be parasitic capacitances, or the capacitance between the gate and channel is known as parasitic capacitance, and it is utilized in dynamic logic circuits. Now, their operation requires periodic repopulation of the internal node voltage. Okay, levels as stored charge in the capacitance cannot be retained indefinitely. Okay, so we need a regular updation. See, if we are using a capacitance, so over a period of time capacitance loses its charge. So to maintain a fixed charge level, we need to continuously refresh it by electronic pulses of voltage or current. Okay, so this is what means the operation requires periodic updation of the internal node voltage levels, as stored charge cannot be retained indefinitely. Therefore, these requires clock signals to control the charge refreshing. So, a particular time period is observed for which charging and discharging of capacitance can be calculated, and after a particular time period the circuit is automatically refreshed with current or voltage signals, and this is done with the help of the clock signals. Okay, the capability of temporary storing is static, that is voltage level at capacitor nodes allows to implement a very sequential circuit with memory functions. Okay, so the capability of temporary storing a state or voltage at the capacitor node allows us to implement a very simple sequential circuit with storing function. So we can store data in this format in this type of devices. The common clock utilized in this circuit enables to synchronize the operation of different circuit blocks. Okay, and since we are using a common clock in these circuits, so we can even synchronize different memory elements or different blocks of pass transistor logics to work in cognizance with each other. Okay, and since the number of transistors in these circuits are reduced, therefore they occupy a smaller chip area. Now this is the basic structure of the pass transistor NMOS base pass transistor circuit. Okay, we will see about it. The parasitic capacitor may increase the power consumption, but due to the reduced overall silicon area, the overall power consumption is lowered. Okay, now we know that since we are using parasitic capacitances, so capacitance causes an increase in the power consumption of the circuit. However, since the number of transistors is lower and lower, therefore, or we can say the less number of transistors are being used, therefore the overall effect of parasitic capacitance can be ignored. So basic principle of pass transistor circuit, here shows a circuit figure along that is in this circuit is shown a basic NMOS dynamic MOS logic circuit consisting of NMOS pass transistor driven by another NMOS transistor. So we have shown an NMOS pass transistor that is driven NMOS pass transistor that is driven by another NMOS pass transistor. Okay, the pass transistor A is driven by a periodic clock signal. Now there is a periodic clock signal here which drives this transistor, and depending upon the clock values this transistor is switched on or off. Therefore it acts as a switch to either charge, okay, or charge down the parasitic capacitance Cx depending upon the input signal levels of Vin. So depending upon Vin we can charge or discharge this capacitor. Okay, therefore there are two possible operations that can take place. Okay, if the clock signal is active, that is this clock is high, then logic 1 transfer charge up the capacitor Cx to a logic high value. So if this clock is high, so this Vin is directly connected to this capacitor, okay, because it is an NMOS, so it will be open when clock is high. So this Vin will appear across this capacitor and this capacitor will charge. Now logic 0 transfer is charging on capacitance to a low value. So when the clock is low, this transistor is off and this Vin cannot come across this transistor. So slowly and slowly this capacitor will discharge through this path and logic 0 transfer will occur. In either cases, the output of depletion load NMOS inverter is obviously assumed as low logic or logic high level depending upon the voltage of Vx. So this depletion load NMOS will take the value depending upon the voltage at this node Vx. Okay, when the clock signal becomes inactive, that is when clock is 0, the pass transistor ceases to conduct and the charge stored in the parasitic capacitor continues to determine the output value of inverter. So till this was on, so we can have V in here, this will always be on, but once this NMOS is off, so depending upon the value of this capacitor and this node value Vx, its functioning will depend. So even if input is cut off due to this capacitor, this NMOS can keep on working or functioning. Okay. So logic 1 transfer has been shown here in a very simple format, Assume that the soft node voltage Vin is equal to VOH is sequential to 0 initially. So at Vx is equal to 0 voltage it is initially. So our NMOS will be off. So as logic 1 is applied to the input terminal, which corresponds to Vin that is equal to VOH that is equal to VDD. Now the clock signal at the gate voltage goes from 0 to VDD. So if this signal is applied at this input and clock signal goes from low to high value, then the pass transistor becomes active, and this node starts to charge the capacitor. Okay, so the variation in node voltage can be plotted as this graph, that it will be charged to a maximum of Vmax, but it will be not exactly Vmax, and it will be little bit less, that is VDD minus VTN. The voltage rises from its initial value of 0 volt and approaches the limit value of large T, but it cannot exceed the limit value of Vmax, that is VDD minus VT. The pass transistor will turn on when Vx is equal to Vmax, since at this point the gate source voltage will be equal to the threshold voltage. Okay, therefore the voltage at node X never attains the full power supply voltage of VDD at logic level or logic 1 transfer. Thank you.